excitement in the air. We are getting there slowly. You get it? I can't wait. You know, I should be frank with you. I can't wait. Really, what I would want to teach you would be beyond the standard model, you know, what I do for my living. We used to have a course here, Beyond the Standard Model, many years ago. Real physics of Beyond the Standard Model. I felt it was too much. I'm a minimalist, so I believe you should learn little and learn it well. So we would discuss, you know, we get together and we discuss which courses should be there, and I would say, look, less and less. So I gave an example. I said, let's get rid of my course. And we did. But then also there is supersymmetry, which is there. Remember, supersymmetry is pure speculation, as beautiful as it is. But it's not a must anyway, so we shouldn't. There are certain things beyond the standard model that will be little must. Like neutrino mass, as you know, has become a must now that we know. We may have to say a few words, but in order to do that, we have to sort of finally define the standard model. So maybe by the end of today or on Monday, we'll see. Because we are getting there. Apparently, you didn't have any questions last time, no questions now. You understood the Higgs? It was there, right? We found a way. And the whole trick was just to going from one basis to another, from one gauge to another. And it somehow seemed to work, naively speaking. But what we need to be sure that you grasp is the actual connection between broken generators and in this case, massive gauge field. So we should do a few non-abelian cases, so non-abelian Higgs. So let's take the example of SU2. Our simplest, most natural, the obvious, the first test of our knowledge of group theory, right? This is all we learned when we were little was spin, right? Spin was all about SU2, and now we go to that example. That means I take a doublet. So phi is a doublet, which means as it transforms as U phi, as we said so many times, U is the SU2 transformation, which I can write as e to the IH, which I can then write, which is Hermitian. So it is simply my usual basis. I immediately generalize this the way I write to any representation of SU2. It stops being really SU2, strictly speaking, right? Because I can take even a 5-dimensional representation. This was supposed to be SU2, but when I say a doublet, this is really SU2 because TA is a Pauli matrix. So the Lagrangian for my Higgs field is the same as before, only it's a covariant derivative. I won't even write the potential. You saw it so many times that there is no reason to write it anymore. It's the same potential I took in a global case. The physics of particles that I'm studying, okay, their mass properties and so on are hidden in the potential, okay, the scalar particles. I can forget completely about the gauging, right, because the potential is the same. And what is missing is the kinetic energy that you know we write in many different ways. I can write it as a trace or explicitly as the basis. You've now done that. And A is 1, 2, 3. What else?
You could add the fermions.
I could add the fermions. I will have to do that. Let me just at the moment, of course, this will be important. Notice it would be interesting if I had the fermions, okay, that there would be a little challenge here. Let's comment it on in a minute. Just to check what we expect. What did we learn in the global case? What happened in the global case, remember? Tell me. I don't want to write anything, I just want to see whether you remember. Oh, sorry. I should write it just because this was the potential. So the vacuum manifold, okay, I can remind you of that, was phi 0 dagger phi 0 is v squared over 2, which was a three-dimensional sphere, as you told me. What happened then? What was the outcome? We said that SU2 breaks down through the vacuum expectation phi 0 to
Nothing.
what was happening? Nothing. Everything got broken, okay? And we knew that because it was easy to see that TA acting on phi 0 was not going to be 0. There is no way a Pauli matrix can annihilate a doublet, okay? All the states in a doublet carry spin, if you wish. That's another way. There is only spin half and spin minus half in a doublet. I'll do it in a second later. If I take a triplet, not all the particles carry spin in the triplet, right? Because there is 0. When it's odd, there can be a 0 hidden there, okay? Then the symmetry breaking is different. So, so in other words, I expected 3 massless Nambu-Goldstone bosons, right? Sure. Broken generator, massless gauge field, so I expect, so there are 3 of them, I expect 3 Nambu-Goldstones. Anyway, it's easy to see. All I had to do to write phi as e to the I GA over V 0 V plus H over 1 over square root of 2. And I found immediately there were 3 massless guys, right? I expect 3 massive gauge bosons. So this is really another way of writing it. I could write this as e to the GA over V phi 0. This is phi 0 plus something, right? Inside is phi 0, you agree? I can do I told you sometimes it's good to see explicitly that the physics does not depend on the choice of phi 0, something that is to us intuitively clear. So let's see, let's just take now for the moment, so let me take the vacuum, forget the G's at the moment. Anyway, I know they are not physicals, right? I can rotate them away. They don't exist. So I could just go for the moment in the vacuum to see what I will get for the gauge boson mass matrix. I will get from the kinetic energy d mu phi 0 written like this. Derivative is 0, so I'll have minus I G over 2 TA A mu A acting on phi 0. Symbolically written. Let's write immediately what this is. This is G square over 4 phi 0 dagger. This is what I mean, of course. TA A mu A TB A mu B phi 0. It's actually written here, right? Which is 1/2 1/4 G square V square. Phi 0 square is V square over 2. But I don't care about the form. All I know is V square over 2. I didn't put it in this form. Just to. And then I have, no, I'm rushing. Or am I? No. Not fair. just write like this. I'm sorry. G squared over 4, there should be phi 0. I told you it was going to be a bad lecture. I'm still making up. Phi 0 dagger. Maybe I need a little break. Maybe at some point we decide to have a 5-minute break. And I get myself another coffee. Let's see if I can hold through it. So this is phi 0 dagger. This is TA, TB. Why did I write 4? Why did I write G over 2? Nobody objected. Oh, you're saying because I didn't write the covariant derivative. It's all, okay, I can do anything I want, it's true. It's a funny definition of G. Well, it's not correct, but normally we do this. So there's no 4. Let me correct myself here. The way I've written, there's no 4. You agree? Phi 0, A mu A, A mu B. Now, this is G squared over 2 over 4, phi 0 dagger. I could have written immediately sigma A, sigma B, phi 0, but I don't know what's wrong. A mu A, A mu B. Is it of nice? I have a generic formula. This could have been some other vacuum of a large representation. I could play it a little bit. In a particular case for a doublet, it's very simple, right? Because Pauli matrices, I know what this is. This is delta AB, you agree? Plus I epsilon ABC, sigma C. Agree? Well, this term doesn't contribute. This is symmetric. Manifest. So we get, I continue here, delta AB, so I'll get G squared over 4, phi 0 dagger, phi 0, A mu A, A mu A. 3 massive gauge fields. I'm summing over A. When I don't say anything, of course, I'm summing over A.
I guess you do the you're on the phone.
Sorry?
But that's because of the TA equal to.
We guessed correctly? Well, it has to be because we got rid of these guys. I can simply get rid of them. And I can't lose degrees of freedom. These are what we call would be Goldstone boson, would have been Goldstone boson. These strange phases that get eaten by massive gauge fields. I need 3 extra degrees of freedom. They went into the masses of the 3H guys. So let me be more specific. I can write this as 1/2 G squared over 4 V squared A mu A, A mu A. So find out that the mass over MA is 1/2 GB. And they all have the same mass. Well, this is very strange. This is what often we do, and sometimes we don't find the answers. But most of the times we do, right, in physics, what we do. We are puzzled when something is equal to something else. If there are 3 of us having the same mass, we will be very puzzled. I broke the symmetry completely. There is a very strange result. When I break the symmetry, I expect the masses to be different. There is no SU2 anymore. I'm claiming they get the mass because of the symmetry breaking. So it's very strange that by breaking the symmetry completely, I'll get 3 masses the same. Let's remember it, okay? Because I'll give you an example now when I break less symmetry, and yet I get more different masses, or less same, because they're all the same. So this is a sort of puzzle. It's good that the number is 3. So I could ask, why is MA1 equal to MA2 equal to MA3? You know, usually there is a symmetry behind equalities. way of saying it, when something, is zero or the things are equal, usually then I go and find the symmetry, okay? I don't know whether it's a good language or logic to say that the symmetry is responsible, but there is a correlation between the fact and the symmetry. Let's put it this way. So that's for you to pause and think why. It's not easy. This is a very, very non-trivial question. But the answer is, okay, to help you, yes, there is a symmetry. So you would have to see something highly non-trivial. I broke the symmetry, but I didn't break the symmetry. It's like Nambu, who tells C and Yang, yeah, you're right. Yes, I have a mechanism of breaking the symmetry. Like he says, but you told us that it's not broken. Yeah, true. He says, no, it can't be. Well, this is an example when I break the symmetry, but I don't break it. But not in that sense. But you see, I wanted to tell you what you would have known. I could have chosen a vacuum in one direction, you could have chosen in another direction, or in both directions, or whatever. You nicely see that you get the same result, okay? I told you sometimes we'll show it explicitly, when it's easy. When it's not easy, I leave it to you for an exercise. Okay, in order to compare, by the way, you noticed, okay, this case, when it comes to H, it's the same physics we did in the Goldstone, in the double Goldstone case. So I don't have to write it anymore, right? The physics of the H boson, we already know it, you and I. And maybe it's just good to say it here, I'm sorry. Although I said it, this would have been V plus H squared. Anytime you see V, remember there is always V plus H squared. That's the definition of H. It's the field that lives around V. Okay. So if you see somewhere written in a book or written, someone gives you a listener to a talk and someone is just looking at the vacuum, you can immediately, you don't have to write everything else, okay? It's been derived already. V gets accompanied by H. So again, the H would couple to gauge bosons proportional to their mass, right? That's the same as in the U1 case. The physics of what is going on, both Nambu, Goldstone, or Higgs, it's all captured in the U1 case. There is nothing to learn anymore when you go to non-abelian examples, except for some group theory. That's why U1 is so important, and I wanted you to sort of grasp that. Oh, I could say that phi is a triplet now, still call it SU2. But it becomes sort of SO3 in my example, if I call it a triplet. And I could do this. I can keep the same U. Since I like to work with U, then I can say that phi transforms as, if I keep the same U, I can write it as a matrix. We call it adjoint. And it transforms as, let's call it sigma. Just to have a different name. It's a triplet now. Triplet I can write as a vector, as a column. I could write it as a row, that's up to me. I have to organize my knowledge. Or a joint. What is a joint? I told you a joint is everything. We'll never talk about vectors anymore, because how in the world do I talk about the vector of SU5? I mean, it's also some vector with 24 components. I don't have a neat notation for that. Sorry? Here. There was no convincement. UDEC. This is a unitary. This is how I study. Correct. where now sigma is a, what is it in order to transform? Is it a column? Is it a, it's a matrix, right? Sigma is a Hermitian matrix, which is traces because that's irreducible. The trace is invariant, so I can get rid of the trace. Right, this is my vector. We said we'll do it like this. And we know that there is always one representation that transforms like that. This is gauge boson that cells are actually an adjoint. Why? Because there is always the number of gauge boson is equal to the number of generators. But this is obvious here. If I have a Hermitian traceless matrix, I can write that sigma is phi A. I can introduce components and expand in the basis of the same generators I introduced. Now I could write the potential. The potential would be lambda. It's now real, so let's put it here. Trace sigma square. What is trace sigma square? It's 1/2 times the vector. You see, it's a vector, right? Because there are 3 A's. This is my normalization, okay? Key A are Pauli matrices. That I never changed. Remember what I said, if you know Pauli matrices, SU2, you know everything. I can do SU5. All I need to know are Pauli matrices. I don't have to remember anything else, okay? I'll always write like this. In my TAs will always be Pauli matrices. I'm just going to be playing where I put my Pauli matrices. I have sufficiently many places to put them and can generate the group, right? You did in SU3, you did like that. And on top there is always Cartan. So I could write this minus V square over 2 square. Or I could have written 2 trace square minus V square. Let's write like, I don't, it's irrelevant. It's just a normalization. Remember V itself. It doesn't have a physical meaning because people say in the books that this is a physical parameter equal to 174 GV or something in the standard model. You will see in another book they say it's 248 GV. That depends how you normalize it. Here is physics. I can rescale this. If I rescale my V, I will get a different relation, okay? I may get MA equal GV. Right? We could call this 1/2. We could immediately say this is, you know, GV Yasset. I don't know. Without the half. You say, I don't like your half. Okay, so for me, always the physical scale will be mass of the messenger. It's nice to think of the scale of weak interaction as the mass of the messenger that is causing it, right? So we say for the electromagnetic interactions, I don't have that scale, right? Photon is massless. So what is the symmetry broken to? You told me the other day. It should be, you know, it should be here, not in SO2, right? Because I can write, so M0 is trace sigma 0 equal V square over 2, which is sigma phi A0 equal V square, and this is called S2. How do I know that the symmetry will not be completely broken? Well, I can write sigma 0 as V before I write, I can say it immediately. I know immediately that whatever group I take here, and this is a trivial example, the rank cannot be broken because I can always take sigma 0, whatever it is, it transforms under my group in the following manner. Therefore, I can always choose this to be diagonal. It's a Hermitian matrix, it can be diagonalized. These are now numbers, these are not fields, right? So I'm allowed to diagonalize. That's like choosing the direction of a vector. I take sigma 0 in the Cartan subspace. But it's just one matrix, sigma 3. In other words, I could write sigma 0 when I do this would be V times sigma 3. Or maybe the way I normalize 2 trace sigma squared. Maybe V over square root of 2 would be better. You agree from here? Trace sigma 3 square is 2, not 1. No? Yes. I think it's good. Okay. It's just a name for V, but I think I think they match. It's all about matching. And that tells me that in this direction symmetry is not broken, right? Remember what we said for the adjoint. That you can still speak over generators in a general manner, and that is acting on the adjoint. It's just a commutator, obviously. Because from here I will get a commutator when I expand. We've done this before. And therefore I conclude immediately that T3, which is sigma 3 over 2, that P3, when it acts on sigma 0, which is sigma 3 over 2, sigma 0 is 0. Sigma 3 commutes with itself. That is my unbroken generator. So I expect 2 massive gauge bosons. And let me not do this exercise, okay? Because we should leave something for you. Tell me, what do you expect will happen? Of course, in that direction, I will get a massless gauge boson, right? Because the gauge bosons pick up mass from here by acting on the vacuum. When the generator annihilates the vacuum, so the doublet case, we found that MAA is, doesn't matter how we normalize, but they were all the same. Remember, same. In this case, well, one thing to say is a theorem, if you wish. If TA acting on whatever field on a vacuum, I write it generically 0, in that direction gauge boson will be massless. How can you get a mass? The only way you will get a mass when this acts on a vacuum. But if you give 0, the guy is massless. That's what I expect, because the only way for me to get a mass, I have to break the symmetry. It's like saying if you don't break the symmetry, gauge boson is massless. Of course, that's what happens in QED. There is no Higgs boson in QED that has a vacuum excitation rate. So in this case, tell me what will happen. So now going back to my SO3 adjoint. now doublet. I join the equal triplet. What should I get? How many massless gauge bosons? One. Call it Ma3. What about the other two guys? They will be massive. You check that. I don't want to do it well because 1 and 2 will not commute with the vacuum. The 1 and 2 goes through sigma 1 and sigma 2, but the vacuum is in direction sigma 3. Sigma 1 and sigma 2 do not commute with sigma 3. But without doing the calculation, tell me, do you expect the relation between their masses, these two? Sorry?
Masses should be the same.
Why?
Because direction 1 and 2, none of them is preferred over one another.
Why? I agree. You're almost there.
Because they are the same footing. If you take the vacuum between the direction 3, direction 1 is not more important than direction 2. So
Right, why? What do we say that? We have a language of physics.
they have a rotational symmetry.
We have a rotational symmetry around the third axis. We call it SO2. There was SO3 got broken, right? If I choose a vector in this direction, everything must be invariant under the rotation. So without doing a calculation, please check it. You must get this equal to Ma2. True. You can do it either now if you're playing, you know, as I keep speaking. I don't even know why I'm doing these exercises. This is sort of obvious. We actually did the global case. We found there were two massless Nambu-Goldstone bosons. That means, that's what they had. They had the same masses, 0. They had to be two of them with the same mass because there was a symmetry in this direction. And we actually saw it, where you have a Nambu-Goldstone boson, you get a massive gauge field. That's all. It eats it. The fact that it's non-abelian doesn't change anything, you agree. It's always a question of that particular generator that you already had in U1. So notice, in the SO3 case, we say that the symmetry here gets broken down to SO2 through the vacuum expectation value of my joint. There is less breaking. This is milder. I got something outside. In this case. And yet I have less symmetry in the masses. 2 equal, completely different from the third. By the way, this is a kind of example we like to think about for physics, right? We need to have a photon. If I want to build a standard model, if I don't get a photon, I have to go back to square one. I'm not thinking right. There has to be, at the end of the day, it has to come out that there is a massless gauge boson. So this is an example of what the world should look like. Some guy is massive and one guy. For example, this could be a W boson hidden here. W boson has 2 components. It's a complex field, for example. But here, you know, I ask you, so how come I got more relations about masses without any protective symmetry? Here we say that there is a protective symmetry. We can say that SO2, we can say is protective. Protective in what sense? It protects the masses of 1 and 2 to keep them the same, make sure. So you see, if I know group theory very well, I don't have to compute always. Or it's very good before when you do the homework, when you have little research in the future or more research. Try always to think before doing the calculation. It will help you eliminate mistakes. If not, if you don't manage, at least when you do the calculation, check it with, you have to be somehow able to see it, why you got the result when you get it. It's always going to be group theory. So this is what I expected, that when I find the equality of masses, I expect that there is a symmetry behind that. So once again, why not here?
Can you introduce a new symmetry, like
No.
weak isoscale?
No, it's what I write. The symmetry is not what I say. The symmetry is what I write. Let's remember. Of course, often you do the following. You say, I want to have the symmetry. My name is Glesher, and I postulate the symmetry. So you are saying, well, actually you do, because I have a symmetry that I postulated. But be careful, however, someday you postulate the symmetry and you write down the Lagrangian. You may have more symmetry or less than what you thought. It's like choosing the right variables. Another advice is don't be wrong. Very easy to be wrong. I'll show you. I've often referred in papers that were wrong in that sense. The authors say we have this symmetry, but actually have more symmetry. And this is the example of a doublet. So let's go back to the doublet. There is a hidden symmetry. There is more symmetry than what I said. Let me make sure that this is clear. Any question on a triplet, please? No, I can erase. At some point during the day, you have to go over the triplet and see. If you're not familiar with this, you have to come back to me, whether in my office or talk to me. You have to be able to use the Bissedia joint, as I did the other day. I will never go back to the vector notation. Okay? So let's go back to the doublet to see what I actually asked you to with the doublet phi. I wrote the Lagrangian. Let's go back again. d mu phi. Let me write symbolically, square, minus V of phi, minus kinetic energy. Of course, the symmetry in question here is the one that I do postulate. And it has to do what I write for the covariant derivative. Once I write the covariant derivative, d mu is d mu minus Ig sigma A over 2 this tells me what the symmetry is, right? It's defined here. Once I write it, this generator satisfies SU2. This is really SU2, no more and no less. There's no way I can be wrong here. Right? I could be wrong here, though. You see, V of phi is phi dagger phi. Well, let's say better. I don't even care. It's a function of phi dagger phi because of invariance. We wrote it quartic. Well, to whatever order, it's always a function of phi dagger phi, my SU2 invariant. Agree? And then we said the vacuum had to be something. You told me it was S3. Why is it S3? How do you see that this is S3, this equation? Right in components. So write a doublet. Say, let's use R because R tells me that they are real. Then what is phi dagger phi?
R1 squared sum of
I don't care really the vacuum now. This you actually knew that there were more components. That's how I got the vacuum. There are actually 4 components in a doublet, not 2. What is the symmetry of this potential? It's not SU2 what I thought. See how you can be wrong. What is the symmetry? SO4. SO4 is not SU2. SO4 has how many generators? 6. Remember, the generators can be taken as anti-symmetric in SO groups. It's Nn minus 1. Has Nn minus 1 generator. SO3 has 3. SO4 has 6. So the symmetry here, this potential has an SO4 symmetry. And SO4, we said 6 generators. What is the rank? In SO3 is 1. You have only one vector in one direction. In SO4 you would have 2. The algebras with the same rank and the same number of generators turned out to be equivalent. This is actually equal to SU2 cross SU2. Do you know how to show this? All of you? If you don't, go back and show it. All it means that you take some linear combinations of SO4 so that they commute. But this you have to know. This is what I mean by knowing group theory, not knowing fancy group theory. This, how do you also, what is another way of knowing this? That you've done already millions of times. This is Lorentz group in Euclidean space. In a Lorentz, in the Minkowski space, that's rotations and boosts. And the boosts were just like SU2 except for some factor y. Well, if everything is Euclidean, then you have rotations, boost is a rotation. That's where I get SU2 cross SU2. You understand this? Just another little exercise, okay, that I'm suggesting here. This will always be useful, you know. Try to think of Lorentz often as what, you know, what it would look if time was not, didn't have this error, okay, which doesn't bug you very much, okay, it bugs me more than you, but slowly and surely it will start bugging you why there's the error of time in this direction. I don't mean just as physicist. But it's a beautiful question of physics, right? Because all the micro laws, that's a strange thing that somehow describes the world. All the laws are invariant in time going to minus time, except the microscopical evolution of the universe, right? But that's a different story, not relevant today. So actually, there was more symmetry to start with. Now what will happen? What happened when I took an adjoint? Look what happens in SO3. In SO3, I rotated the adjoint in one direction, or I can rotate a vector in one direction. So I will always have this symmetry around that direction, unbroken. So what will happen in SO4?
That's to SU2.
Sorry?
Should break to SU2.
Yes. SO3, precisely. Why? Because you can choose it in one direction. Doesn't matter how you write. In that direction you can't break. In other words, what I write here, I can write phi 0, that was my 0. 0 plus I0, that means 0, and then here V only. But you see there are 3 directions where the thing is 0. And there will be no breaking. I don't want to do it again. It's not the lack of sleep that I mentioned before. It's just that it should be obvious and that you should do it if you don't see it. But it's exactly the same thing, right? SO127 breaks into SO126 when you take the vector. You will just choose it in one direction and everything else, except for the direction, will be broken. So you see, I said that I broke SU2 to nothing. This is true. As far as the gauge structure is concerned, really it's true. I broke SU2 down to nothing through the vacuum expectation value of 50. The number of broken generators is 3. What happened in the potential is a little more subtle. But the answer must be the same. And it is. I've broken 3 generators, notice. I'm actually right that the 3 were broken. Because this had 6 generators, and this has 3 generators. And so there has 3 broken generators. This is correct, like here, there are 3 broken generators. 3 broken. So even if I looked at this potential, when I found there was an accidental symmetry. Accidental symmetry got broken, but something remained. This thing that remained is often called protective, of custodial symmetry. This is called custodial. This symmetry SO3. Why? It's sort of the thing that protects these guys. Someone very smart saw this, right? It took a little thinking, but with the knowledge of group theory, maybe you will figure out, because they were puzzled. This is one of those nice issues when it's good to ask yourself why something is 0 or equal, okay? Sometimes it may not take you far, that depends, we can talk about it. But it's good to know, it gives you a reassuring feeling that there is a physical reason for this strange accident. At the end, because you see the symmetry breaking is determined by the potential. Potential tells you how much symmetry breaking took place. This is where we read off these things.
So if I try to break the symmetry with a more complicated or alternative potential, I would lead to calculations.
You may lose this protective symmetry, right? You're saying, what happens if I bring another doublet? Now the situation, of course, will change dramatically because you may not have a protective symmetry. You have to rethink everything, okay? Let me not do it now here. We can maybe try to take a more complicated example, but precisely this is the issue. That in general, whatever you conclude from that simplest field that you took will always be changed in a more complicated, even just by adding more of the same field in principle. In practice, I don't know. I don't want to answer this question now without you and I doing an explicit example, but I don't want to now make it more complicated. I would like to make sure that you understood this.
And this custodial symmetry is not physical because just inside the potential doesn't define the kinetic parameters.
Right. It doesn't do anything for us. At the end, the counting right. In this case, it doesn't do anything precisely because we broke it all of it here where it matters. You understand what Victor is saying. In the end, I'm reading off the physics from the kinetic energy, or this is what the number of the gauge boson and so on. It may be useful just in organizing my knowledge. You're saying whatever I do that comes from the potential, I should get the same number. So it's very useful. There are these symmetries that are useful, although they may not play a role in the dynamics. And these are typically global symmetries. They are very useful, but they don't tell you anything about dynamics. Isospin is very useful to organize your knowledge in strong interactions, for example. The properties of the pions and the nuclei, right? Pions have almost the same mass, proton and neutrons almost the same mass, very useful symmetry, but it doesn't really give you dynamics. So to say it's not physical, let's say it may play a physical role, but it's not dynamical. I'm a little worried when I express myself not to confuse, not just you, not to confuse myself. tend to be a purist, and I'm often, when we discuss and work, people always tell me that I care exaggeratedly about the language. I think you can never care too much about the language. It's obvious that the way you see the world will influence your language. That's obvious. But Chomsky became famous, one of the people Wittgenstein before, thought of worrying. Depending on the language that you use, it will form your view about the world. There is also this interesting other direction, okay? This is why it's good to worry about the language. So somehow I'm here reluctant to say that it's not physical, let's say. It has no dynamical role. Doesn't affect anything except tells me things like this, right? That I can use. Okay, maybe Victor is right in saying it has more mathematical use of helping me guess the results.
Yeah, what I'm thinking is that it's non-physical because it's not related to anything
Right.
that propagates the use of freedom.
It's
just
true.
Somehow administration.
It's true. It's true. Once said clearly like that, then I agree. Okay, then the language becomes, to some degree, secondary when we are sure. And I can even forget about it. All that I learn that I have this nice thing that explains this, but I got it anyway. I didn't have to be really smart. Okay, didn't change anything. True. The calculation of masses was so easy that you wouldn't have had very much to say. You don't have to calculate the masses that will come out to be the same. It takes you more time to realize this than to me to compute the masses. So, but I wanted to talk about that because I like to be reassured when I see things like this. It's sort of nice. There is always a little discovery. Even in a homework there may be a little discovery. We often talk with the people who like to do what some of us like to do, to keep staring about your results. There is always something there. And this is a typical example, right? You get a result and you say, no, I got to understand. But was it clear? There were a number of statements here. Let's go back again. So this is what I meant. The symmetry of potential is not what you say. Remember that there will be a tricky homework on SU3 and the adjoint. Just remember, the symmetry is not what the guy, the professor says is. We don't care who she or he is. The symmetry is it comes out. So we said there must be more symmetry because actually I have 4 fields. And the SU2 invariant becomes SO4 invariant. The breaking, fortunately, does not depend on realizing this at all. Because SO4 must be broken to SO3. That was the second statement, right? Which is obvious. And you can see it in the adjoint. So adjoint is very good in SU groups. In SO group vector, maybe, it's not hard to write a vector in the SO group, right? Because you write a column. So you should be able to go from one to another. For example, if I write it as a column in SO4, then you would say that phi 0, sigma 0, I don't know how we write it, would be 0, 0, 0, V. Obviously, SO3 remain. Nothing is broken here. Right? This is an interesting thing to know. By the way, this may be worse. Saying a few. When I have a doublet phi, which is phi 0, I could write it like this. Sometimes you will see it. Or I can write it as phi up, phi down. It will turn out to be, when we do the standard model, there will be charges, will be the positive of phi up, phi down. Well, at this point there are no charges, so maybe this is a good notation. Let's take phi up, phi down. In SU2, when you have a doublet, you have an anti-doublet, you agree? But the anti-doublet, actually, we call it phi tilde very often. You remember what it is?
I sigma 2 times.
It's actually given, this is normalization, I can put any, I sigma 2 phi star. This is also a doublet. Okay? This is like charge conjugation in a Lorentz group. When phi transforms as u phi, then from here phi tilde transforms into I sigma 2 u star phi star. The u star you can commute. It's trivial because of the property of Pauli matrices. This is equivalent to saying the phi transpose I sigma 2 phi is invariant. And it generalizes to Lorentz. Remember in a Lorentz group there is this charge conjugation? But it's just anti-symmetrizing matrix. It really just like I sigma 2. Okay? It's very easy to check if you forgot, we actually checked it in your first homework. You've done that when you went into a two-component basis. So let's do something funny. Let me write a matrix. I hope I do this right. Let me introduce the matrix. How will I call it? Now I need a smart name. Sigma was in a joint. I'm just thinking what to use for this matrix. I already used 5 capital and 5 small. I'm sorry. Let me do this. He doesn't care. Yes, he's not writing, so you don't care whether I change notation or not, right? Maranur may care. Yes, excuse me. So let me write this not as, you will forgive me if I write like this. And then phi tilde would be, what is phi tilde? I sigma 2 phi star, so help me, what will it give me? That will give me d star minus u star. Agree? So let me introduce the matrix now, which is phi tilde. It's a little stupid what I'm doing, very cumbersome. Sort of poor man's way of... it's not completely stupid though. I hope. If I get this wrong, I'll stop, okay? So, let me take the trace of this. So phi dagger, so let me write this matrix. What is it? That's UD D star minus U star. So from here phi dagger is U star D star D minus U. Am I right? Thank you. So let me write what this trace is. What do I get? I get u squared plus d squared twice. Notice, however, that phi dagger phi is u squared plus d squared. Obvious. That's the famous SO4 symmetry. This is R1 squared plus R2 squared plus R3 squared plus 4 squared. We are there. So notice that this is actually equal to 2 phi dagger phi. So I can introduce some stupid matrix and I will see that actually is the same invariant as I wrote. Right? My potential depends on phi dagger phi. But I can also write it like this. In other words, well, I don't know why I raised it, no. The potential was a function of phi dagger phi, which is a function of sigma 1 over 4 Ri squared. So this is my SO4 symmetry. Okay? But I can also write the potential to be a function of the trace of well, sorry, this was phi dagger. Now I have to go back to this. Phi is now a matrix, okay? Forget it. Phi is a doublet. A complex doublet. Phi is a complex doublet. This is when you decide to change your notation, but it's done. You agree it's one and the same thing. I can write my invariant as a trace of this funny matrix. But this is invariant. Notice that the trace phi dagger phi is invariant under I can do this u phi v. These are unitary matrices. U dagger u is v dagger v is 1. Notice that the trace is invariant. Right? The phi dagger phi transforms into v phi dagger phi, no, v dagger v. Correct? So trace phi dagger phi goes into the trace v dagger phi v, which is the trace of v dagger phi dagger v, which is invariant.
Are you proving that SO4 is S2 process?
Yeah.
Okay.
I wasn't sure how you guys would do it, okay? You can do it by commutation relations, okay? And that's sort of a little boring. So this is a useful trick that you can use, okay? I didn't want to tell you what I was doing. Normally I always tell you what I'm doing, okay? I want you to get there. But I really wanted to see whether you will, okay? Hassan realized, and I'm glad. There's a little trick that can be useful when you do the group theory analogies. You can do a poor man's approach and just check the commutation relation. But here, I've proven that SO4 is equal to SU2. This has SU2 cross SU2 symmetry. Well, you can say you're not proving that it doesn't have more than, okay, obviously, but count the number of generators. There can be no more than this. There are 6 generators in the rank 2. It's interesting, I put phi and phi tilde, you know, I may find this very useful that one day, if I want to have really 2 SU2 You know, maybe I decide to live in the world one day. You see, Weinberg, well, Gleschel says that the world is SU2 left-handed. It's sort of painful, right? Maybe not to you guys. I still can't believe. I could not believe in 1974 when I saw it, okay. Actually, it was Salam who said, maybe the world is actually SU2L cross SU2R. So if I do really believe that this is very useful, then I have already something that I may generalize when I have more than one SU2 groups. You know, maybe I'll put different, I could put one if I need a complicated representation. I can play with this, you see, it's useful really, generically speaking. Why? For us, SU2 is sacred. We all know Pauli matrices. So whatever group you take, if you can rewrite it as SU2 cross SU2, it's always good. As a product of SU2s. Like SO4, don't work with SO4, work with SU2 cross SU2 because you know Pauli matrices. And so on and so forth. Just like I do the triplet as an adjoint. Why? Because I know. And I want to know only Pauli matrices, okay? I want to be able to forget everything else so that I can master very well this group theory that I need to do physics. Okay. I said more than I maybe wanted, but I couldn't resist at this point.
And many times
It was an impulse. I did it at the spur of the moment, okay? I wasn't going to talk about it.
I think that many times when people, give this proof, they actually don't give it for SU2 plus SU2, they give it for SL2 or SC.
Right. You can do it in a, sure. But it's sort of, it's nice to see that Euclidean world would be just rotations, okay? It's sort of. I think that's all I will say. It depends on you. I'd like to move to the standard model. Of course, there is very little time, so I'll just give you an outline. I want us to think now, and in order to think, we should add the fermions. We can do what Sergio asked an hour ago, a little more. But I let the fermion, I'll move from, I could do it here, but it will be even more clear when I move to the standard model, because standard model is a trivial generalization of what we just did, literally. And then the first thing we will do is add the fermions. But see if you want to ask me anything before I start erasing. So here where I've written here, you see? This is SU2 cross SU2. And this would be my SO4. This is invariant, right? Here I could write this. In other words, I could have written phi also like this. R1, R2, R3, R4. And then I will have the symmetry phi going into all phi, where this is 4 times 4. SO. And I've just proven, okay, just to summarize, that SU2 cross SU2 is equal to SU4, SO4. There are a few of these interesting accidents. For example, tell me SU4, how many generators SU4 has? SU4, sorry. 15. And what's the rank? 3, they are traceless. Yeah, you're almost right. See. Then, okay, so that SU4. SU4, you told me, rank is 3, 15 generators, right? What about SO6?
They have the same number of generators.
15 generators. We said 6 times 5 over 2 is 15. You can also see immediately that the rank is 3 if you play with it. For example, SO4 is equal at the algebraic level. Just like SU2 is equal to SO3. and SO4 is SU2 cross SU2, there is another interesting, a passing comment regarding these accidents when SO group. Normally they are never the same. There's a few examples, okay. Anyway, so the standard model, we said, all that I have done this to prepare you so that we can do the standard model, and the idea of the standard model, we said. So now let's talk about the fermions rather than about the Higgs, because it's all started with the fermions, to have a gauge theory of weak interactions. So we said, let's try SU2. Now it's really SU2 as a gauge electroweak theory. We tried and we failed. Do you remember why we failed? I will choose a doublet of fermions, right? My fermions, for example, my quarks would be up and down. That's what I mean by SU2. And leptons would be nu and the electron. Correct? That's the meaning of SU2. That, and you know that for weak interactions there is no difference between up and down quark. Because of that, neutron decays into a proton. W sees a neutron, doesn't give a damn. Sees a down quark, makes it an up quark. Or a neutrino becomes an electron, vice versa. So can this be SU2? So they're both doublets. Both of them are doublets. When I say SU2, and I say a doublet, this is a nice example in which now nothing is anymore in my hands. Okay? Remember, I keep emphasizing that, you know, the Feynman-esque approach to physics. Make a guess, and then see what happens. No more, nothing now. Once you made a guess, it's not in your hands. You're not allowed to keep changing. So can this be SU2? Remember, that means that D transforms as UD. But U is e to the I, TA, theta A. And I just said that TA is sigma A over 2. That means all the doublets in this world transform the same way. And when I say that SU2, that means that my electromagnetic charge lives in SU2. That's what I mean by SU2. And this obviously cannot be. There is only one matrix in SU2 that can be diagonal, and that's T3. This, in other words, Q electromagnetic in this theory would be proportional to T3. I'll just take it T3, it will have to be proportional. This will never satisfy it because these charges are completely different from these charges. So, this is what we painfully admitted. By the way, it's a beautiful theory because in SU2, charge is quantized.
So the argument is that the reason is that the charges in the Q doublet are different from the L doublet, or because the charges inside each doublets are different?
Well, the charges must be different in a doublet.
But
that's the meaning of SU2, the charge. The particle in a doublet cannot have the same charge. Otherwise it wouldn't be SU2. SU2 tells you what it tells you. You know, remember spin. It was plus half or minus half. It couldn't have been both plus half. And by the way, generalize it to a triplet. The triplet, again, you would know the charges. 1, 0, minus 1. Different, all three different, right? This is important. The eigenvalues are different. There may be some invariant. And what is beautiful about spin is that it's quantized. And the miracle is explained by saying that it corresponds to the well-defined group structure. All the spins are proportional to half. Integer numbers times a half. You have spin half, you have spin 1, you have spin 3 half, you have spin 2. So SU2 would have been beautiful because charge is quantized, but not the way SU2 says. So this is a sort of a nice example of a beautiful theory killed by ugly facts of nature. As someone said, I don't know who it was, I think Elios. There are a lot of people who emphasize on the beauty. If you read, I was looking recently, you know, I read these popular books from time to time because I've been itching to write a popular book, so I want to see what other people write. I was reading Frank Wilczek's popular book. They're worth, some of them nicely written. There are some great popular books. There is one that stands out for all seasons. It's Weinberg's First 3 Minutes. It's mind-bogglingly serious, profound, and if you don't know cosmology, go and read the first 3 minutes. I could enter, I worked at symmetries at high temperature. I've learned everything in the beginning, you know, because we were not taught cosmology at that time. It was not so serious as it is today. It was still developing, so it wasn't a part of a course. Of course, it wasn't in the curriculum. Beautiful big books, and then there are some of them which are lighter, which are more, even Weinberg's First 3 Minutes may be really hard on a layman, or a lay person. But so at the end, you know, Wilczek will emphasize, a lot of people do, you know, no, beauty always wins. I know some examples, I'll tell you when we come later in the standard model, but it still bug me. Well, I will show you manifested a deeper and a more beautiful theory, killed by ugly facts of nature. Now this one will maybe correct for in the future. We'll see. But why is it painful? Because then Gleschel says, well, if it doesn't work, I will enlarge it. You have 2 options now when your beautiful idea doesn't work. Give it up, or admit that it has to be a little less minimal. So it says add U1. So make the theory to be SU2 cross U1. Let's see, you know, this is the approach. This is really the Einstein cartoon, New York Times. And you see Einstein very happy. This literally is that. Sometimes it works. Now, and I asked you the other day, and it wasn't clear immediately to you. Okay, if doesn't work, can this be electromagnetic? Remember, it couldn't be because the definition of this, let me call the generator of this guy Y. Don't ask me why I call it Y. This is a definition of this. So Y cannot be electromagnetic. Because then the guys would have the same charge, and they don't. As we just said, what Victor asked, in SU2 they would have, of course, different charges. If it's all coming from outside, they will have the same charge. For example, I know, you know, because this commutes with color, I can tell you immediately, this guy must have the same color as this guy by definition, if he commutes with color. And that's why I don't have to talk about the color. Because, you know, W is color blind. And photon is color blind. Which means that the charge must be a combination of the 2. Don't ask me why I call it Y, and don't ask me why I put Y over 2, okay, and not Y. I could put arbitrary coefficients, but this is arbitrary. All the beauty is gone. There is no charge quantization anymore. It becomes the same old miracle that bugged us always. This is an arbitrary continuous number. Of course, now it's very hard to fail. because you give me the charge, I'm going to look for the right Y. Why I'm doing that is obvious, right? Because I want to agree with what nature tells me. Now, two things I learned, and this is why the fermions are very important, that weak interactions, however, we write like this. Why? Because it's left-handed group. Why don't I just write like this? Left-handed equivalent to weak interactions are left-handed equivalent to the fact that the W boson, this is some normalization, couples to say U L bar gamma mu dl, only left-handed, plus nu L bar gamma mu el, only left-handed guys. Okay, we are getting there. Good enough for today. That means that these guys are left-handed. It's not true that the fermions are doublets. Sometimes they are, and sometimes they are not. For example, it's true for the left-handed guys. So in other words, for the left-handed guys, so I should be very careful what I mean here. So let me write it here. I can write TA is sigma A over 2. This is what I mean by doublet. It's defined through the action of generators on these states. What about the right-handed states? I need to introduce right-handed states. They must be singlets. They don't have weak interactions because W is hidden inside SU2, which I've given up, by the way. It's not SU2. It's this case here. Let's write it here. Now this may be a little less beautiful theory and it won't be killed by ugly facts of nature. Okay, it lost some of its beauty, but it will also impress you with a number of predictions that will emerge. So you said this must be singlet. So I cannot organize it together. I must write like this. So here it means that TA is 0. There is a wall I cannot cross. This is the crux of the problem. This is why we are studying Higgs mechanism and all of that. Remember, I need symmetry in order to, whether it's hidden or not, it's a different story. Whether it's broken spontaneously or not. But it has to be there to start with. So the whole development, if you wish, starts here, and it's beautiful. The importance of parity violation cannot be overstressed. In order to appreciate, because it's not appreciated, it's people learn the standard model, and of course it works very well. And then every Dick and Harris, these days starts their paper or their talk saying that standard model has this problem and that problem, which is crazy. And what is lacking is the appreciation for the magic that happens. So what you and I will do, we'll first develop this. Then when we go back and imagine the world in which Li and Yang were wrong, we will imagine the world which is parity conserving, and you will see that we'll all fail down. That it's really a magic of experiment and theory that somehow, as it happens in a profound theory, makes it work. And what I need now, I have to break a symmetry because I cannot write fermion masses even. Why? Because the fermion mass, FRF, whatever the fermion is this. But this cannot be written, right? Because it wouldn't be invariant. It's manifestly breaking SU2. Here this is a doublet, here is a singlet. And this is what we start on Monday. It's time to wrap it up. Once you get this idea, Well, first there is a beautiful physics that follows just from the group structure that I'll do on Monday. I don't want to do it today. So two things we have to do. I want you to understand the physics that doesn't require Higgs at all, and a good amount will follow just from the group structure, and the other that requires the Higgs, because you can guess the Higgs now, you can see. Just go back to 1967 and ask yourself in that afternoon, what Higgs do you have to use? Because you never know what Higgs to use just by mathematical exercise. What should the Higgs be? I just say this and so.
You mean doublet or what?
Or what? Yeah, I'm asking what, how to know what to choose. Is it a doublet, triplet, quintet? Doublet, why? Why does it have to be a doublet? You will see when we do the physics beyond the standard model as an outline, you'll have no idea really what Higgs to take there. But here, fortunately, so how do you develop a new theory, right? What does Einstein have to do? He has to agree with what Newton told him. So Weinberg has to agree with what the world told him, fermions are massive. So he has to write the mass term for fermions, but he cannot. But he can, because we've learned. How did we do it in the one case? You remember what we did? So all I have to do here, instead write FL bar, FR, some Higgs.
So then it will be raised.
And it will be, I have to, otherwise I'll never have a theory, okay, unless I do that. And that tells me it has to be a doublet. Because this is a doublet, this is a singlet. So Higgs is a doublet. So it's good that we learn all that we've learned today, you even custodial symmetry and so on and so forth. You will learn more about the doublets. I will try to repeat all the essential features because I have to do it now in a deeper level by doing the standard model. Okay, so let's leave it for Monday. We'll be able by Wednesday to get the essence of what the standard model is all about. Then there will be a lot to study, of course, to get the nitty-gritty, but at least the essence next week will be kind of crucial. Any last question? One, two. Just do it.